Today we're talking about error detection using LRC, also known as Longitudinal Redundancy Check. LRC applies parity checking across multiple bytes vertically, like checking the columns in a matrix. Each column of bits is parity checked, and the result is stored in an extra row called the LRC byte. That LRC byte is then appended to the data, and the whole thing is sent as a packet. Let's see an example with even parity. Data 1 is 10110010. Data 2 is 01101001. Data 3 is 100101111. The calculated LRC is 01001100. So the packet is the 3 data bytes plus the LRC. What are the pros and cons? On the plus side, LRC can detect single-bit errors and some multiple-bit errors. For example, if we flip a couple of bits, say data 2 becomes 011011101 and data 3 becomes 10110111, the new LRC is 011010000. Because the recalculated value doesn't match, we know there's an error. But LRC also has weaknesses. It can miss certain 2-bit errors that occur in the same column. For instance, going back to the original packet, if data 2 changes to 01001101 and data 3 changes to 10110011, the LRC ends up the same as before. This means the error goes undetected. So to summarize, LRC is simple and useful for catching many errors, but it's not perfect. If you enjoyed this explanation and want to learn more about digital design and error detection, make sure to hit subscribe and support the channel.